Thank you. Welcome to our webinar today. We are especially excited about this webinar because this is our first international webinar. I'm happy to introduce our presenter today, Bruno C. Sousa. Bruno received his PhD in statistics, graduating from the University of Michigan, and now he teaches in the Department of Mathematics for Science and Technology at the Universidade do Minho in Portugal. Dr. Sousa is speaking with us today from Portugal. He is the coordinator in his program there, in a program entitled Census in Minho. It's a project where students apply the skills that they learn in their mathematics classes to real data sets. Dr. Sousa has an article in the current issue of Stats Magazine about estimating the size of a population. It's titled, How Many Fish in the Sea? And that is his topic for today. Dr. Sousa, we turn back over to you.
Thank you, Paul, for the lovely introduction. And hi to everyone. I hope you can hear me okay on that side. And I just want to thank you, everyone, for being here. And I hope you enjoy it. So it will be my first webinar. International also, and also national. So let's see. So just be patient with me, and let's see how it goes. So I'm going to talk a little bit about capture-recapture sampling, and so the outline of my presentation will be I'll talk about what's needed and how to do capture-recapture sampling. I'll go and try to simulate a little bit these methods in Excel so that it can be very easily done with students in class. And we'll talk a little bit about the problems, and please just, participate as you wish and ask any questions that you may want to do it during this presentation. So starting, what's needed for capture-recapture sampling? So basically, we're used to, when we're talking about sampling, we're used to the traditional methods like simple random sample or stratified sampling or cluster sampling or any other methods of sampling. The difference between capture-recapture sampling is that in the previous one, you always know the size of the population, and you take a sample from this population. In capture-recapture sampling, so basically, your goal is what you want to estimate is actually the number of individuals in a population. And for this, basically, you might be interested in knowing how many animals, such as birds or fish or insects or any other kinds of animals that you might think, or even, for example, the number of minority individuals. And this is important, for example, to know the number of homeless in a city so that you can possibly in the future do some adjustments of undercounts in the census. How can you actually do it? So basically, you capture a first sample from the population and you mark individuals captured. So you can do it in many forms. So you can do it with a ring, or you can do it with a collar, or any kinds of procedures that you might think. Or maybe you don't even need to mark individuals. For example, when you're counting, for example, whales, they have their own identity to identify the specific animal, and you don't need to mark them. So after an appropriate waiting time, you do a second sample from the population, and this sample should be selected independently from the initial sample, and you actually count the number of recaptured sample of the marked individuals from the first sample. So the key steps here are the first capture, then you mark individuals, then you do a waiting time, an appropriate waiting time, and then a second capture. Between the first and the second capture, the waiting time is just to make sure that the two samples are drawn independent of each other. Okay? Here's my first question. Can you actually perceive any problems with these kinds of samples? Do you think, for example, if you capture the first individuals and then after 5 minutes you do a second capture of the individuals, do you think it's appropriate or not?
There could be a problem if that individual hasn't had the opportunity to mix back in the population.
Absolutely, absolutely. So the waiting time is actually just to make sure that on the second draw, basically, you have another represented sample of the population. So you don't capture the same individuals just because you didn't give them enough time to mix within the population. Again, thank you. So what should we expect, basically, from doing this procedure? So what do you think if the second sample, so if we wait enough time for the individuals to mix among the population, what do you think if the second sample is represented of population, what do you expect to happen in terms of these marked individuals from the first sample and the marked individuals in the second sample?
Shouldn't the probability,
Go ahead.
Shouldn't the probability of selection of the second sample be proportionate to the ratio of the individuals in the population?
It should, because what we have in the first sample, we mark the individuals that we captured.
Mm-hmm.
So we know how many individuals that are marked in the population. Okay? So in the second sample, the proportion of individuals that are marked from the second sample should be approximately the same as the proportion of the marked individuals in the population. Okay? So just to make it easy, let's do it in a more mathematical way, and let's see what we have. So we have capital N, which is the unknown size of the population. So we don't know how many individuals we have in our population. The N1, real N1, so we have the size of the first captured individual. The ones that we're going to have, that we're going to mark in the first capture. After that, we take a second sample of size M2. And in this sample, we count the ones that are marked. Okay? So all of these quantities are known except for N. So we have capital N in red that is unknown, and then we have all the three other quantities that we know. So as Paul said before, what we expect to happen is that the N1 over capital N, which is the proportion of marked individuals in the population, should be approximately equal to the proportion of marked individuals in the second capture. So if we see that, it's just N1 over capital N should be approximately equal to R, the recaptured individuals, over the number of individuals that we just captured the second time, N2. So since only N is unknown, we can basically solve this equation and we get a possible estimate for the population size is equal to N1 times N2 over R. Is that okay?
That makes sense.
Make sense? can you actually see a problem in this formula or not?
What happens when one of them is 0? It's I 0.
It's size 0. Which one? R, exactly. So that's one of the problems with this estimator, which is, so for example, imagine that you do a first capture and then you wait too long to do a second capture. So what happens is that you might, in the second capture that you do, you might not get any of the marked individuals. So R can be 0. Is that correct?
Yes.
So this little r can actually be 0. So let's see what we have. So to solve this problem, there are other estimators that are proposed to as estimators of the size of the population. And I'm going to give an alternative one, which is, I believe it's less intuitive, but actually solves the problem of when r is equal to 0. Okay? And I'm going to call this n tilde, and it will be written in blue, and it's just given by this formula. As you can see, basically, here, if r is equal to 0, the number of marked individuals in the second capture, then the estimator, there's no problem with the estimator because it's no longer going to be equal to infinity. Okay? So what I'm going to do is how we can simulate this procedure using Excel. So let's see what we have. So for our simulation, I'm going to consider that I have a population of size 250. So I know N, capital N, and that we're going to randomly mark 50 individuals of the first capture. So N1 in this case is going to be equal to 50. For the second capture, we're going to choose now only 25 individuals. So our N2 is going to be 25. And within these 25, we are going to see how many of these were captured, were marked. And this will be our R. Which is 250. It's the size of our population. We do the first marking of 50 individuals, so N1 is equal to 50. And then we do a second capture of 35 individuals, and we count the ones that are marked. So let's see how we can actually do this in Excel, okay? And how can our students basically reproduce this very easily. So now I'm going to go over the Excel, and can everyone see the Excel?
Yes, Bruno.
Yes? Okay. Yes. First of all, I have to apologize. You're probably seeing the Excel is the Vista one, but it's in Portuguese. Okay? So I'm going to try to read you. I think the menu should be similar in English. So let's see. So we have a workspace here, and what I did, I did in two parts. So the non-population, and the first thing that we're going to do, so let me go back to the slide. So after you have a feeling what the Excel workspace looks like, let me go back to the slide, and let's just go over the first step. So this is just a technical comment. So basically, just to make sure that every time that you do something on the workspace, the random numbers do not change constantly. So what you can actually do, you can go to the options menu, go to the calculations, and just check manual. So the random numbers will only be generated when you actually press F9. So on the first column and on the column A and column E, we're going to insert and generate the random numbers. And this will help us to select the individuals that we're going to mark on the first one and the ones that we're going to capture the second time. So let me go back to the Excel and do that for you. So what you're going to do on the random number column, I'm going to write the word in Portuguese that stands for random, but basically what you're going to write will be random, okay, and then parentheses and parentheses, okay? And it's not going to work in mine because it's not in English, so I'm going now to write it in Portuguese. And let me do it for you, and let's see. And basically what you just have a random numbers between 0 and 1, okay? So after that, you're going to generate all this throughout the 250 individuals and until the color right here. And then you can see, just copy the same number that we generate in the first one. So now if you press F9, now you have different random numbers throughout the 250 individuals, okay? I'm going to repeat the procedure on column E just by doing Control Copy and Paste. So you again have the random number. You go down until the last one, and again you press F9 and you have random numbers, okay? So after you do that, and I'm going back to the presentation, after you do that, basically you need to assign an identifier number to each individual. And we're going to do that by, in column D, selecting 1 through 250. So let me go back to the Excel. Okay, and so we're just going to assign 1, 2, 3, and so on. And after this, Excel is smart enough, and we can drag this down. And here it is. We have 250 members for the population. Okay? Are there any questions? Okay. So the way that we're going to basically select the individuals to be marked is by ordering column A and B according to column A. Okay? So, and then we're going to mark the 50 smaller cases according to column A. So let me do that in Excel so that you can see it. So what we're going to do now is to select the first two columns and then just order by the random number column, okay? And so what we have from the smaller random number to the largest random number generated, okay? So what we're doing here is that you're giving equal probabilities of any individual to be captured the first time that you do your capture of the individual, okay? The first one, the first 51, those are the ones that we're going to be marked. And so we will go all the way down, and I believe it's right here, 54. So we have 50 individuals in this population that are actually marked first, okay? So here we have our first captured and the 50 individuals out of the 250 in our population that are marked. Okay? So let's go back to the presentation and let's see what's the next step. So as you can remember, and I'm going to the previous slide. Let me see which one. No. Let me go back a little bit. Exactly. So we've done the first part, the first captures, and we marked individuals, and now it's like we wait a little bit of time and we do the second capture. Okay? So let's see what we should do in the, sorry. Yeah. So let's see what we have next. So for the second capture, what is basically we call both column B and C to the first three captures in our sampling procedure. So let's do that, and I'm going to copy both columns B and C right there. Control C, and one second, and paste. And so now we have the random numbers for the second one. We can reproduce another series of random numbers by pressing F9, as I did. You see the change in the numbers, and the way that you do it is basically just sort columns E, F, and G according to the second random number that we are generating. And we're going to see what we're going to obtain in the Excel. And let's see, I'm going to sort my second captures according to the random numbers. Let me go back. Order by, again, the random number, and let's see what we have. Okay? So, as you can see, we are going to look at the first 25 smaller numbers. And I'm just going to change these a different color. Okay? Okay. So we have the second capture, which was 25 individuals, and we can actually count the individuals that are marked in the second capture. So we have 1, 2, 3, 4, 5, 6, 7, 8, and 9 individuals that were marked and were captured in the second capture of our population. So what I've produced here in Excel is just a table that I'm going to write all the numbers, all the simulations that I've produced. So if you press F9 again, you are going to see that we have 3, 6, and 9 individuals. Okay? So I'm going to write here on the table next, so the number that were recaptured, which were 9. And of course, if you press F9, then it's going to be calculating the estimates using the first estimator and S, with the one that had a problem with R, and the second estimator and tilde, the one that did not have a problem with R. So R could be 0, that there was no problem. And as we can see now, we have an estimate of the population which is equal to 138.9 and 131. Pretty close, but the NS is a little bit higher than the N tilde. Okay? Any questions so far? Okay, so you can reproduce these steps very easily just by, I'm just going to take the columns here, but just by pressing F9, as you can see, we can, and ordering again the second and calculating this again, we see that now the first 25, the ones that I'm selecting now, we only have 4 individuals that were recaptured the second time. So we can actually put the 9 ones and the 4 ones and calculate again. And we see that in the second simulation of the procedures, now we have an estimate of 312 and 264 for hand test. So this time n tilde is much closer to the true value of the population size. Okay? So is everyone okay with this step?
Looks good.
Okay, looks good. So we can repeat this many, many times. I've done this 100 times, for example. But what I usually do with my students, and you can do it, the way that it will work in your class, but basically what I do with my students, when I'm with the Excel, basically they do 3 or 4 times each of them, and then they come to my computer, and they basically fill in the values. Let's say in the next one, someone recaptured 5 individuals, and then the other one recaptured 10, and then 6, and then 8, and so on. So we can actually see how the values actually change from simulations to simulations. Okay? So at the end, what you have lots and lots of simulation, and basically you have many different results, as I'm showing you now here on the table on the right side. And as you can see, they vary from perfect simulation, which is this one that I'm highlighting now. For n hat, you have 250, exactly the population size, but a little bit lower for n tilde. Okay? So, yes?
Can I ask you a quick question?
Absolutely.
Just to clarify, column J is the column that has the 100 iterations, right?
Column J, exactly. The 100 iterations, exactly.
So, yeah, there it is. That's what I want to see. Thank you, Bruno.
Absolutely. So basically, this yellow part is just, just to make it easy to count the numbers, okay, of the recaptured individuals, our R, okay? So if you have a class of 30 students, if they do 4 or 5, then you have plenty of simulations already. Okay? So let me go back to the presentation now. And basically, at this time, you can address many of the questions to your students, depending on the level that they are in terms of statistics. But actually, you can ask them, with their 4 or 5 simulations, what conclusions can students take from their estimates, okay? And, for example, if you do go to the first, and let's look at the 4 results, okay? And I'm going just to highlight the different colors so we can concentrate on these values. But basically, students can ask, what kind of the population size could be if they got so many different results. They have like a result of 400 individuals and a result of 150, more or less. So they can be a little bit not being very trustful in their results, and they might suggest, doing more and more simulations to see what's the behavior of these estimators, okay? So if your students do have more knowledge in statistics, or you can introduce new concepts to them just by, for example, introducing histograms of the estimated values. And, for example, you can do the interpretation of the behavior of the sample distribution of these local estimators and discuss how well they behave in terms of estimating the true population size. You can also try and talk a little bit about confidence intervals, although it is a little bit tricky when we're talking about confidence intervals for these estimators, and I'll talk a little bit later about this issue. So let's just try a little bit of this process and see what we have here in our simulation. So what I just did, I went to the 100 results that I generated, and I construct an histogram of the estimates that I obtained from the first estimator N hat for the population size. So if you had to guess the size of the population from this histogram, what would be your guess? Anyone wants to try?
I'd guess somewhere between 2 and 250 on that.
Sorry?
Somewhere between 2 and 250?
So, something between 2 and 250, I would say so. Because, you know, like, we can introduce here concepts as the node, for example. The node of this, the class, the nodal class is just 250, isn't it? So this is the most frequent value, more or less. But definitely, you know, values between 350. Let me do the pointer. Can you all see the pointer? Yes. So values that are far away are very less frequent than the ones around here. I think will be a good guess. Okay. So let me show you the next histogram that I produced with 100 simulations from the second estimator. Okay, the one to avoid r equals to 0. So what do you say about this one?
I'd probably guess around between 200 and 250, maybe a little higher.
250, absolutely. Now a final question, I think. If you had to choose between one estimator and the other one, which one would you prefer to estimate the population size?
I like Sousa. It seems like it seems like maybe there's a little bit less. Actually, I changed my mind. I'm not sure.
Not sure. Okay. I would, you know, just try to ask students to try to give some reasons why to choose one or the other. And actually, I think both of them, as we can see, you know, the shape of the distribution is skewed to the right, so they're not centered around the true value. So another concept that we can introduce here in our students is the concept of being an unbiased estimator, okay? Mm-hmm. For example, you might argue that N tilde will give more extreme results than the estimator of, the N hat will give more extreme results than the estimator of N tilde. So it seems more or less that the N tilde, the values are more concentrated around the 250 than the N hat, okay? Mm. So these are the type of questions that you actually might introduce with your students and try them to discuss and argue and to defend, so you can create, like, for example, two groups, and one would have to defend the N hat and the other one will have to defend the N tilde. And they might talk about what kinds of problems they might obtain with one or the other. So another way to see, to compare the results of these two estimators is just by plotting the results of the 100 iterations. And in this graph we have in the x-axis we have the 100 iterations, and in the y-axis we have the values, the estimated values for n. Can you see the colors okay? Can you see the green one?
Yes.
Oh yeah, that's good.
The green line and the red line. Is that okay?
Does the green line represent M tilde?
The green line actually represents M hat.
That's M hat, okay.
Exactly. And the red line represents M tilde. Okay? And now you can see like the blue line. Is that correct? And now you go like one. So the blue line is the true size of the population. So the 250. Okay? So by looking at this graph, what we are able to see is actually they're pretty close to each other. Is that okay? Looks okay?
The green doesn't have as many extreme values. I mean, the red does not.
The red does not, which is M tilde, okay?
Right.
So with this graph, I think we're pretty much okay by saying that, you know, when an extreme value happens, it's more likely to happen in the N hat than in the M tilde, okay? So you might be lucky and you might get a value close to the true population size, but if you're not lucky, what happens is that the M tilde will give you a much higher extreme value than the M tilde, okay? So the N hat, which is the green one, will perform poorly compared to the M tilde, okay? So these are the types of things that you can actually try with your students and try to make them discuss, you know, the different results that they obtain using two different estimators to estimate the population size.
Mm-hmm. So these are important concepts too that students don't often experience in their introductory statistics education.
They might not. So some of these concepts are actually a little bit complex. I agree with you, Paul. But I think, you know, even if they don't have the concepts yet, it will alert them to these issues. Okay?
Right.
There's not one optimal way of doing things, you know. And when you think about the two estimators, of course, the first one is very clear and very intuitive, but it actually has some problems, and one of the problems is being biased towards the true value of the population, and there are other ways that we can solve these problems, okay? And you might not be able in an introductory course to explain all the complexity behind this process, but it definitely makes them, I think, it makes them think a little bit about these issues. So, all things very wonderful if we can do that, but there are actually some problems with this capture. There's lots of problems with capture and recapture sampling. It's a very hard issue to discuss actually. Can you think about some problems that might come other than, for example, not waiting too much time to do the second capture? Can you think about that or not?
What about conditioning of the animals that you're capturing?
Conditioning on, in what sense, Paul?
What if they get scared the first time you capture them and they go away?
Exactly. That's one of the hardest problems to deal with, and that's what we call actually the trap shy, which is the problem that we're suggesting, which is they run away, they get very scared, and so basically what happens, after being captured the first time, the probability of being captured the second time is much lower compared to the rest of the population. Okay? Or you can actually have the opposite problem, which is the trap happy. So let's imagine that you feed them so the first time so that you can capture them, and they get very friendly with you because we're nice people, and they don't go away, okay? So which means that you have much more, a higher probability of these individuals of being captured the same time than the rest of the population, okay? So that's the problem between these two behaviors of the individuals, and what you think will be the effects on the estimations of the population size. If you look at the formulas, what would happen with the trap-happy behavior? What do you think it will happen? So with the trap-happy behavior, what do you expect on the second captures? You expect to get many individuals that are marked or not? Yes. Yes, isn't it? So what happens is that our R in the second capture will be much larger than what it should be. So what happens to the estimates of the population size? Are they going to be above the true value or below the true value? Above the true value, exactly. So with the trap-happy behavior, what we're going to see is that an underestimate of the size of the population. So the trap-shy behavior, which was what Paul was mentioning the other a minute ago, you're going to get exactly the opposite behavior, an overestimate of the size of the population. Is that okay?
Explain that again, please, Bruno.
Okay, so let's see. The trap-happy behavior, our R, which is the marked individuals in the second capture, is going to be large, isn't it? Because they don't get away from you. They don't get the food that you're going to give them in the second capture. Is that okay?
Right.
So R is going to be larger than what it should be, and our N is going to be lower compared to the true population size. Is that okay?
Thank you.
Yeah. And the trap-shy is exactly the opposite way. R is going to be smaller than what it should, and what it makes is that N is going to increase if the individuals are trap-shy. Okay? So what I'm going just to do is just to show you very quickly a simulation on Excel, and how I just did it, just in a very easy way. Basically, I did exactly the same thing. So generate the first 50 marked individuals. So on column C that you see right here are the first 50 individuals. Okay, and what I'm going to do, I'm going to copy those here, and the only thing that we'll do is that we increase the probability of these individuals to be captured. And what I just did, I'm just going to press F9 so you can see the difference. Let me see. Let me do. Are you seeing the changes in columns? So I generate a random number, and basically I say, okay, if these individuals captured the first time, so I generate a number. If the number is less or equal than 0.2, then it's going to be recaptured again. Otherwise, it's going to not to be recaptured again. And so I generate many of these simulations and count the numbers that are going to be recaptured on the second sample, and calculate the values exactly the same way that I did the other way around. And we're seeing here the results, and I will go down so you can see the 100 iterations that I produced, okay? And you can do that with the students. Again, you can ask each of the students to do 5 and then fill in your computer, and then just draw the graph, do the same kind of interpretation that you did for the first one. And let me show you what were the results that we obtained. And here are the results for n hat, for our estimator, and here is the result for n tilde. Okay? So, what would be your interpretation in this case? By looking at these histograms, what do you think? Are they trap shy or trap happy? Trap happy, exactly. I also agree. They are trap happy because what you see, the majority of the results are above or below 250. Below 250, exactly. So we clearly see here an underestimation of the size of the population. Is that correct? Right. Exactly. So what we have here, we have, results from a capture-recapture where the individuals are actually trap happy. Okay? So, and again, students can do that. They can compare the results, and we still have the problem of the distribution not being symmetric around the true value, and that's a different issue. So, what I would like just to say some final comments. What I believe, that capture-recapture basically can be used in many different situations in real life. It can be used for estimating the population size of any kind of animals, basically. It can be used, like, for example, a certain species of trees in a forest. It can be used in many applications, and you can use that with your students to actually see how everything works with capture-recapture. It has many problems and many details that you need to be careful, and that's very exciting because things can go wrong, but I think you can learn a lot with what can go wrong, and that's what's exciting about this. You can solve this problem, you can try to improve it. So hopefully with a student project as this one, you can actually spark some lively discussions among your students. And by doing in Excel, I think you can allow students to practice on their own and actually experiment with this concept. Okay? There are many other issues that are interesting here to see, and many other questions that can be answered here. And for example, you can create different groups with your students and make them experiment with different population sizes, okay? If instead of talking about 150 population individuals, you can try and do a 1,000 or just a small population like 50. And you can try, for example, different size for the marked individuals and different size for the second capture individuals, and see what's the behavior of the results that you get. So there's lots and lots of things that you can try with your students, and I think it's a quite interesting subject. And I'll be willing to discuss with you if you have some questions and some more ideas that I can try with my students. So thank you for your time, and let me know if you have any questions. Thank you.
Thank you, Arno. That was a wonderful presentation. Yes, indeed. That's a fascinating topic. The method that you have shared with us today is an easy way for students to learn a very important concept and do it in a hands-on way. They can experience the process of estimating the number of fish in the sea by doing fishing in Excel. A great idea.